Since we saw a few limitations with our Pearson correlation coefficient, let's come up with a new measure of correlation coefficient which does a better job than Pearson correlation coefficient, especially when you don't have linear relationship. So Pearson correlation coefficient is very good when you have a linear relationship, right? So can we somehow fix it? Can we somehow fix this when you have slightly nonlinear relationships? Not like sine curves, but at least when you have data sets like this, right? It's not perfectly linear, but it's monotonically non-decreasing relationship, right? When you have relationships like this, is there a way to fix it? So again, this is the page for on Wikipedia for Spearman rank correlation coefficient, right? So just to give you a quick overview of it. So let's say for this data set, for this random variables x and y, my Pearson correlation coefficient is 0.88, but my Spearman is perfectly 1. So first let's go through the mathematical concepts of what a Spearman rank correlation coefficient is. So I've just drawn a simple tabular data here just so that it's easier for us to go through it. So let's assume I have collected height and weight, my random variables x and y, for 5 students, right? And let's assume these are my heights and these are my weights, heights in centimeters and weights in kilograms, right? Now what rank correlation coefficient says is, instead of using your x and y, let's create a new random variable. Let's call it rank of x and rank of y. What is rank of x? Rank of x is, take all of them, sort them. The smallest value will get a rank of 1, right? So which of them is the smallest one first? 140 is the smallest one, so it gets a rank of 1. Which is the next smaller element? It is 150, so it gets a rank of 2, right? So this rank is nothing but if you sort your x's, where does each of your data points lie? Just on the x-axis, that's all, right? So which is the third one? The third one is going to be this, so it has a rank of 3. The fourth one is this, and this is the fifth one, right? This is the rank of x. So I'm creating a new random variable here called the rank of x, right? And similarly, I can create rank of y. So of all these, which is the smallest? This is the smallest, right? 46 is the smallest, so I give it a rank of 1. The next smallest is this, I give it a rank of 2. The next smallest is this, and I give it a rank of 3. Here I give it a rank of 4, and here I give it a rank of 5, right? Now what Spearman rank correlation coefficient says is, why don't we simply compute your Pearson correlation coefficient of rank of x and rank of y instead of computing your Pearson correlation coefficient on x and y? Because ranks are strictly increasing, right? If you think about it, ranks are strictly increasing. So let's see what happens. So that's all. Spearman rank correlation coefficient is basically Pearson correlation coefficient of ranks, and rank is calculated as I just explained right now. So let's see what happens when we apply Spearman rank correlation coefficient. So this is your data set. So if you take 2 points here, so let's assume I take 2 points here. So this is strictly non-decreasing, right? Suppose if I have points x1 and x2 here, and the corresponding y1 and y2, I know that rank of x1 is going to be greater than rank of x2 because x2 is slightly greater than x1, and rank of y2 is going to be slightly greater than rank of y1, right? And the relationship is going to be more linear. Suppose if you have a strictly increasing function, right? If you have a strictly or monotonically increasing function, which means as x increases, strictly y is increasing. The relationship could be linear or non-linear, I don't care. So like for example, this is a strictly non-decreasing function or almost a strictly increasing function, right? Now in such a case, as x increases, your y also increases. So whether your relationship is linear or not, Pearson correlation coefficient will give you a value of 1 as long as x increases. Let's say as x increases, if y increases, doesn't matter whether it's linear or not, right? Your rank correlation coefficient is going to be 1. Similarly, if x increases, let's say y strictly decreases, linear or not, right? Your rank correlation coefficient is going to be -1. If x increases and y increases, if the relationship is linear, only then your rho is going to be 1. If this is only linear, it's going to be exactly equal to -1. So what rank correlation coefficient is basically saying is, I don't care whether things are linear or not, but as long as there's a strict monotonicity, I'm going to give it a value of 1. Now that helps us a lot. Rank correlation coefficient is my favorite correlation coefficient because it doesn't care about how far points are, how close things are. It only cares about the rank, right? So let's take a data set like this, right? Or let's take this is a better data set. Yes, this is a very interesting data set. In this data set, between x and y, you almost have a perfect, almost linear relationship, except for a bunch of outliers here. What happens in this case is your Pearson is going to give you a much lesser value. Of course, we know that the relationship is almost positive. So this value we know is going to be positive, right? But this value, what is the ideal thing? Because there are only a bunch of outliers, you would expect it to get a value very, very close to 0.9, because this is not again a strict line, or it's not strictly monotonically increasing. So what Spearman correlation coefficient does very well is, if you have a small number of outliers or extreme points, it handles the data much more elegantly by giving it a correlation, the Spearman correlation coefficient is 0.84, while Pearson would give it a much smaller value of 0.67. So Spearman rank correlation coefficient, because we are going away from what these numbers are, and because we're going into the space of ranks, right, on where a point is, right? Spearman correlation coefficient is much more robust to outliers than Pearson correlation coefficient.